All right, let's dive into one of the weirdest, most fascinating ideas in all of physics, wave-particle duality. Seriously, this is a concept from the quantum world that completely shatters our everyday sense of what's real and what isn't.
So take a look at this. You see these rings, right? It looks just like the ripples you get when waves spread out and interfere with each other, a classic diffraction pattern. But here's the kicker. This wasn't made by light waves or water waves. It was created by firing a beam of electrons, tiny individual particles, at a target. So how on earth can a stream of particles create a pattern that screams waves? Well, that's the big mystery we're going to unravel today.
So here's how we're going to do it. First, we'll look at this puzzling pattern. Then we'll meet the scientist behind a truly radical idea. After that, we'll see the proof, check out a powerful application, and then, we're going to do the math ourselves. And finally, we'll see how all this forced us into a completely new way of looking at reality itself.
Okay, let's get right to it. This puzzle isn't just some weird little quirk of electrons. Nope. It gets to the very heart of what matter is at its most fundamental level.
You see, in our big, everyday world, things are pretty simple. A wave is a wave, like a ripple in a pond. And a particle is a particle, like a baseball. They're two totally different things. But quantum mechanics just throws that whole idea out the window. It tells us that down at the tiniest scales, everything is, well, it's a bit of both. It can act like a particle one second and a wave the next.
And this whole dual nature thing actually started with light. For a long, long time, experiments showed light behaving just like a wave, making those interference patterns. But then the photoelectric effect was discovered. That's where light acts like a stream of tiny little bullets of energy, called photons, that can actually knock electrons out of a piece of metal. So light itself was the first clue that things could live this strange double life.
And this is where a brilliant young physicist, Louis de Broglie, comes into the picture. He looked at what was going on with light and asked a question that was so simple, it was revolutionary.
That's it, right there. In his PhD thesis, no less, he basically proposed his beautiful symmetry. If light, which we all thought was a wave, can sometimes act like a particle, then why can't an electron, which we all thought was a particle, sometimes act like a wave? It was a massive leap, just taking this weird property of light and saying, hey, maybe this applies to matter too.
And he didn't just stop there. He gave us the math. The de Broglie equation says that any moving object has a wavelength, and you find it by taking this tiny fundamental number called Planck's constant, h, and dividing it by the object's momentum, which is just its mass times its velocity. It's this beautiful, simple formula that connects the particle property of momentum with the wave property of wavelength.
So you're probably wondering, if everything has a wavelength, why doesn't a bowling ball look wavy as it rolls down the lane? Well, it all comes down to scale. For a big object like a ball bearing, its momentum is so large that its wavelength is ridiculously small, like a trillionth of a meter. You could never, ever detect it. But for a tiny little electron, its wavelength is on the same scale as an atom, and that is something we can actually see.
Now, de Broglie's idea was just a wild hypothesis at first, a theory. That is, until a few years later, when an experiment came along and proved he was spectacularly right.
So here's the setup. They took an electron gun, kind of like the one in an old tube TV, and fired a beam of electrons. They aimed this beam at a super thin sheet of graphite foil. Now, the cool thing about graphite is that its carbon atoms are arranged in this perfectly regular repeating pattern, and that grid of atoms acted just like a diffraction grating, the perfect obstacle course to see if these electrons were going to behave like waves.
And would you look at that? This is what appeared on the screen behind the foil. It's the very same image we started with. Those bright rings are where the electron waves added up, and the dark spaces are where they canceled each other out. This was the smoking gun. It was undeniable proof that particles, electrons, really do act like waves. De Broglie's crazy idea was right all along.
Now, this discovery wasn't just some mind-bending physics trivia. It immediately became an incredibly powerful new tool for scientists to actually see the atomic world.
I mean, look at this image. We're seeing individual atoms of platinum. We can do that because we can use electrons as tiny little probes, and they work so well for two main reasons. First, because their wavelength depends on their speed, we can literally tune the wavelength by changing their energy. This lets us focus in on things of different sizes. And second, they aren't affected by the super strong force inside the nucleus, which means they give us a really clear picture of the atom's overall structure.
All right, now for the fun part. Let's actually put this theory into practice. We're going to use de Broglie's equation to calculate some of these quantum wavelengths for ourselves.
Okay, let's do a quick example. Say we have an electron moving at a pretty zippy 2.6 times 10 to the 7 meters per second.
We just take our equation, lambda equals h over mv, and plug in the numbers for Planck's constant, the electron's mass, and its velocity. You run the calculation, and boom, you get a wavelength that's on the scale of an atom. Tiny, for sure, but as we just saw, totally detectable.
So what happens if we speed the electron up even more? Well, as its momentum, its mass times velocity, goes up, you can see from the equation that its wavelength has to go down. It gets even shorter. It's a really simple, direct relationship.
Now, we can also work a problem like this, which is a little different. Here, we're given a voltage. So the first step is to figure out how much kinetic energy the electron gets from that voltage. Once we have the energy, we can use a slightly different version of the equation to find the wavelength. The principle is exactly the same.
And just to show how versatile this is, we can also flip the equation around. Let's say we know the wavelength of a neutron and we want to find its speed. No problem. We just rearrange the formula to solve for velocity, plug in the numbers, and we can calculate exactly how fast it must be moving.
So, we've seen the theory, the proof, and the math. Let's just take a step back and think about what a massive impact this idea had on our entire picture of the universe.
You have to remember, before this, physics was built on this solid, intuitive idea that waves were waves and particles were particles. End of story. Wave-particle duality just completely demolished that foundation. It showed that the old rules just don't work at the quantum level, which forced scientists to build a whole new theory from the ground up. And that theory is quantum mechanics.
So, to sum it all up, just look at the evidence. For light, you've got diffraction proving it's a wave, but the photoelectric effect proving it's a particle. And for electrons, you've got electron diffraction proving they're waves, but we always detect them as single, solid little particles. Both of them have undeniable proof for both sides of their identity.
And that really just leaves us with this final, truly mind-bending thought. We see the world around us as solid and definite, right? Made of distinct things. But the fundamental pieces of that world, they don't follow those rules. They aren't really waves, and they aren't really particles. There's some bizarre quantum hybrid of both that only picks a side when we look at it. So what does that say about the solid reality we think we live in? That's a question physicists are still thinking about today.